this video, we're going to talk about this relay board that I've created. It's used to help students better understand how a relay works. Why do we use relays in a circuit? And we'll look at some diagnostic techniques that might be helpful when you're looking at a relay. Up here at the top, I have a master on switch. So I'm just going to slide that over. And we'll see that we have two separate relays here. So this top relay is a 4-pin single pole, single throw relay. This bottom relay is a 5-pin single pole, double throw relay. Look at some differences between these two. These are the most common types of relay that you would find in an automotive application. So first, why would you use a relay? Up here at the top, I have some text that talks about when we use a relay in a car. Anytime that we're trying to take a low amount of current to control a high amount of current. So if we look at this single pole, single throw 4-pin relay, we'll see that we have a fairly small wire here on the top. That's our coil. And then a fairly large wire here on the bottom. That's our switch. So we can take this small amount of current that goes through this part of the circuit, and we can control a large amount of current that can go through this part of the circuit. So how does a relay work? If we look at this diagram right here, we have these individual pins. This numbering system is set up by the Society of Automotive Engineers. If you have a vehicle that was manufactured in the United States, very likely they will use this designation for our relay, these numbers. Pin number 86 and 85 are the coil. Pin number 30 is typically connected to source. Pin number 87 is the normally open position of the relay. And if it has a fifth pin, like this lower one, it will have a pin 87A, which is the normally closed position. Also on a relay, there's typically a resistor or a diode. Its purpose is that when the magnetic field collapses, this coil creates a magnet. When that magnetic field collapses, we don't want to damage any computer component that is connected either to pin 86 or 85 that's turning on and off the relay. This diode, or in some instances a resistor, is there to absorb that voltage spike and protect the ECU. So the coil side up here at the top is its own individual circuit, pin 86 and 85. On this 4-pin relay here below, I've got pin 86 right here and a pin 85 on this side. The load in this circuit is the coil itself. If I were to make a voltage measurement in this circuit, I would find that I have source voltage right here at pin 86. On the back of this relay is a 9-volt battery. I'm using this just to make it as compact as possible and then make sure that it's mobile. On a car, you'll typically see around 12 volts. If the vehicle is running, it could be up to 14 or 15 volts. I'm going to measure the available voltage right here. These 2 points will tell us what the voltage is at the battery. There's approximately 8 volts, so this battery's been discharged a little bit, but we see that our source voltage is around 8. If I make a measurement here at the B positive, that is 8 volts. So we have source voltage right here. That means that at pin 30, we'll have 8 volts, and pin 86 will have 8 volts on this specific example. If this was in a car, pin 86 would have 12 volts when the switch is closed, and 12 volts all the time because this is a direct connection. On a car, very likely there would be a fuse here also protecting this circuit. If I measure the circuit, if I put my black lead here on ground, and I measure the voltage available at 86, I see I have source voltage, and the voltage at 30, I have also source voltage. Notice that when I turn the switch to the off position, 86 no longer has source voltage, but 30 there is no change. So we're going to treat these as two completely separate circuits. This top circuit that has the coil, the load in the circuit is right here. If I were to do a voltage drop test across here, I would see that the majority of the voltage drops across the coil. That indicates that this is the load in the circuit. Notice that when I do a voltage drop test across pin 30 and pin 87, I do not see a voltage drop. That's because pin 30 to 87 is a switch. When this magnet is energized, this coil, the magnetism pulls this switch up. When it pulls the switch to the up position, I now make a connection between pin 30 and pin 87. That connection is simply just a switch being closed. Rather than me manually sliding a switch or pressing a button, we're using a magnet to pull that switch into the closed position. If we put this in the off position, we'll see now that this is an open switch. So I have ground on this side, the light's not on, and I have the source voltage or battery positive on this other side. Once again, when I turn that to the on position, I do a voltage drop across there, I should drop very little voltage. The load on this side of the circuit is the component that is after pin 87. Notice that here we're dropping the majority of the voltage across this resistor and this LED. To recap, the load in this circuit is the coil. The load in this circuit is whatever we're trying to turn on. Now, in this demonstration board, I'm simply using a resistor and an LED to help us know when we hear or when we turn on this relay. In all reality, on a vehicle, we would use a high current drawing load, like a motor or a solenoid or similar, where we need a significant amount of current to be able to turn it on. We want this part of the circuit to have very little current flowing through it. This might be the wire that goes up to the ignition switch. Then this would be the wire that goes to the solenoid of the starter. A lot more current needs to flow through here. I wouldn't want to have the big wire like this going up through the steering column, and so I use a relay to be able to take a small amount of current to control a large amount of current. In this specific example, we can measure the current in the circuit. So if I put my multimeter over here to milliamps, so I've moved my lead over here to the milliamp section, I'm going to rotate my dial to milliamps. On this specific meter, it defaults to direct current. If you're using a fluke or a similar meter, and this says alternating current, there'll be some type of a button likely to switch that. So this is alternating current. I want to measure direct current. In order to make this measurement, I'm going to put my switch in the off position. That's an important part. Notice this light has not illuminated. I'm going to take my red meter lead and place it on this B positive part. I'm then going to take my black meter lead and place it on pin 86. Your meter should turn that circuit on now. I also can see that there's about 30 milliamps of current flowing through this upper circuit. So that's between B positive and ground. In order to turn this coil on, it takes approximately 30 milliamps. That has to do with the resistance of the coil. So this is fairly typical of a relay in an automotive application. It's important when I'm making that measurement, this switch is off because the current is going to move through this positive lead, go through the multimeter, the fuse in the multimeter, and then go out of the multimeter to pin 86 if we're using the conventional theory of electricity. So that means that the current flows from battery positive to ground. And so that measurement, I'm now turning this circuit on. What I would not do is want to bypass the load. If I bypass the load, that's going to be a significant amount of current. That would be the same as me pressing my multimeter lead to be positive and ground. That will open the fuse on the multimeter, and then I'll have to buy an expensive fuse to replace that. So when I'm measuring current in a circuit, I really only ever want to bypass a switch or a wire, never the load, never bypass the load. I can also measure the current on the switch side of the circuit right here. Now, before I make this measurement, let's think about where should I put my multimeter leads. We talked about that you should never bypass the load in the circuit when measuring the current. Remember, my load is over here. This is a switch. I'm going to be bypassing the switch. Now, this is a demo board, so this is actually going to be very little current to turn this LED on. In a real application, this would be a motor and it would draw a significant amount of current, and I'll show a demonstration of that here in a second. But if I wanted to measure the current, I could put my multimeter lead here on pin 30 and my multimeter there on pin 87. Notice that this specific example only takes about 6 milliamps of current. Now, in a real automotive application, usually your multimeter fuse is not rated enough to measure the current. We're only making this measurement as a demonstration. You wouldn't want to measure the current on the control or the switched side of a relay in a real application. I've temporarily soldered in parallel this DC motor to this load. So now we have two loads. This resistor and LED is one load, and this DC motor is another. Now this is a small hobby grade motor, so it's not going to take a significant amount of current, but we're now going to see that we still can use a small amount of current to turn on this switch and control a larger amount of current. So let's turn the circuit on. And we see, and our light is on. I'm going to turn that back off. Notice now that I'm still measuring the current. If I place my red meter lead here on the B positive and my black meter lead on 86, that's going to energize this circuit. So if we do that, we're going to see, even though we're now using a motor that's drawing significantly more current, notice that my switch side is still only drawing about 30 milliamps DC. If I now bypass, remember I'm bypassing the switch, not the load. If I bypass right here and I put my meter on pin 30, remember before we were about 6 milliamps. And if I bypass this and turn that motor on, we can see now we're approximately 80 milliamps that's going through this circuit. So even though back here, when this circuit was my control side of the circuit, I want to treat it as its own thing. All it's doing is turning on the coil. Once the coil has been turned on, the amount of current that's drawn is not dependent on this coil side of the circuit. The amount of current that is drawn is based on whatever loads are associated with pin 30 and pin 87. So we took 30 milliamps to turn on the coil with both a small load and a larger load. And then when that larger load is turned on, it's dependent only on the load that is on the switch side of the relay. I've removed that motor from this circuit. Let's now go down to this 5-pin relay, a single pole double throw. Notice that it has this new pin 87A. With the switch in the off position, if we look at this diagram up here, we can see that in the off position with the coil de-energized, there's no current flowing through here, this is resting on pin 87A. So with the relay off, this light, this LED is on. I've switched my meter back over to DC volts. If I make a measurement right here, we should see that we have source voltage at pin 87A. 87A is the rest position. Now, if I measure pin 87, we will see a small amount of voltage. When I'm measuring the voltage in a circuit, I'm looking at a difference between the positions. This light-emitting diode allows current only to flow in one direction. If I were to do a voltage drop test here to this resistor, notice the difference between this point here and this point here is 0. If I measure on the other side of the resistor, I see the same value. If I measure on this side of the LED, I see the same value. We're seeing right here that on this side of the circuit, the difference in voltage between these is a very small amount, right? That diode is working to prevent the current from flowing in the direction that would illuminate this LED. But we're not turning this on. That's such a small amount. And that's really only a result of us using an LED. On a 5-pin relay, notice that when I turn this to the on position, then the switch from having 87A be activated, and 87 is now turned on. If I measure the voltage at pin 87, I see that I have source voltage right there. If I go back to 87, we're seeing some of that same things happening with this diode as it's preventing the current from going in both directions. So 87, this one is turned off. So that's a 5-pin relay. Finally, let's talk about some diagnostic techniques that we can use. So, diagnose each side separately. Remember, we're treating this coil side separately from the switch side. They're completely separate circuits. They're independent of each other. So, if there is not a click, we can hear a click that occurs. That's the click of this being pulled and making contact. If we hear a click and the light is not illuminating, that's an indication that our relay is actually switching. So our coil is good. Now, we may have a fault here on our switch, but we know at least that the magnet is turning on and drawing this switch to close against pin 87. So if we don't hear a click, then what we need to do is we're going to be checking at pin 86 and pin 85, right? We would check on pin 86 with the switch in the on position. We would expect to see source voltage right here on pin 86. If we did not get source voltage on pin 86, we might start looking at the switch as one of the issues, or a fuse if there was a fuse in line. We also want to suspect, do we have a problem with the ground, right? This ground is a chassis ground, and so there might be a problem with the ground of the relay itself. So we want to verify the ground, and we want to verify the B positive side. If it is clicking, but it's not working, then we need to check the load side. One of the first tests that I would check is I would verify that I have voltage at pin 30. Pin 30 is connected to B positive. Most of the time there will be some type of fuse in line, but we can see here that that source voltage is there, and then we would check after at pin 87. If the switch closes and pin 87 does not have voltage, that indicates that I've got a problem with the switch part of the relay. If I have source voltage here and I do not have source voltage here, and I verified that this thing is actually clicking and turning on, that's an indication that the relay is bad, right? And if it's not that, then I want to check the ground or the load and so on. And so there's some pretty good strategies right here to be able to help you to diagnose it. So hopefully you have found value in understanding why do we use a relay, take a small amount of current to control a large amount of current, how it works. There's a coil side of a relay, right? The coil side of the relay and the switch side of the relay. A diode is there to protect the ECU from when it turns on and off the relay. We have pins 86 and 85. This is the Society of Automotive Engineer, SAE's designation. 86 and 85 are the coil side. 30 is typically connected to B positive. You will come across cars that do things slightly different. For instance, you might see that 87 is the one that is connected to power and 30 is connected to the load. That's not as typical, but it is a possibility. You also might see that the switch is not on the power side, the switch is actually on the ground side. And so you're going to look at your schematic, but as long as you understand that this is the coil, 86 and 85, and 30, 87, and 87A are the switch side, you should be able to correctly diagnose that. All right, hopefully this was helpful. If you'd like to get one of these boards, you can follow a link in the description.